today, Diffusion models V1, which will be using AI models and Rhino. And this webinar is with Zvonko. Very happy to have you here today, Zvonko. So Zvonko is a computational designer, digital fabrication specialist, and data scientist. He's been involved in a research assistant at the Digital Design and Fabrication Department of the Brandenburg University of Technology and Cottbus, as well as a teacher at the Chair of Biodigital Architecture and Sensoric Sci-Fi Lab at the Technical University of Berlin. He has worked at offices for all scales of design and engineering, most notable at 3XN, doing optimization and fabrication of large projects such as the Sydney Fish Market. Zvonko has been applying machine learning and automation techniques in all scopes and scales of design and engineering. Currently, he co-owns the Berlin-based fabrication studio Pixelid, bringing his experience in AI and ML to the physical world. He has been involved in many workshops, webinars, lectures aiming to popularize the use of computational practices. So before we hand it over to Zvonko, everyone here, if you want to chat, please make sure you're switching the chat to say everyone. I see a few of you are writing now and not writing to everyone. If you don't write everyone, it's just going to me. So make sure you switch chat to everyone. And if you have questions during the webinar, please use the Q&A button. If you see where all your Zoom buttons are, there's one that's called Q&A. You can ask questions there. Zvonko also, if you want to switch your chat to everyone, just so you don't forget. This way, if you have anything to send them, they will get it. And just a reminder that this webinar is recorded, and the recording link will be sent by email afterwards as described in the registration form and website. Keep in mind that not everyone learns at the same pace, and we want to give you as much content as possible. So if this webinar is too fast for you, or you're having a hard time keeping up, just feel free to sit back and watch, and you can always come back to the recordings afterwards. But it's important that we get through the materials. So without further ado, I think we could hand it off to you, Zvonko. Also, just a reminder, Zvonko, on your end, if you can speak up into the microphone as you're teaching. I know as the time goes on, our voices can tend to trail off, and it might be hard to hear. So just keep that in mind to make sure they can hear you. And yeah, if you want to start by sharing your screen, you can just make sure that's going.
Okay, so, but you can hear me now. It's all good. It's fine.
Yeah, I think you could, if you could speak up a little bit more, could be good.
I'll just bring my laptop closer to the microphone. Probably that would help.
And also a reminder to everyone that this is an AI webinar. A lot of these things are beta, so we can expect some things to not always go as expected. So.
And that's how it goes with AI.
Yeah. You want to share your screen?
Yep, I'll do it now.
Okay, we can see your screen, and yeah, and if you have anything you want to share with them, you can just paste it into the chat. Just make sure you have your chat on everyone. Well, okay, I'll be here in the background, and I'll let you get to it.
Okay, I will turn off the video so it gets better, the connection. Okay, so I can't follow you in the chat and stuff like that. So if you have any questions or something in the meantime, like just raise your voices if you're here, or there are some very, very important questions. Anyhow, great to see you guys. And what I wanted to start off with, actually, is that like right now we're gonna be doing like a, a long um, talk. Actually, I mean, first of all, we're gonna start with building some models. All right, installing the models.
We only see your desktop. Is that what we should be seeing?
Ah, wait. Sorry. Um, now you can see it.
Yeah, now we see.
Okay. So, as you can see, and of course, yeah, to make it a proper introduction, like I'm Zvonko Vugreshek, and like I have been dealing with. I'm supposed to be an architect actually, but I have been dealing with computational design and AI and digital fabrication and robots and printers and whatnot for like 7 years now, probably. Like, I worked at 3XN, yes, in Denmark. That was my first real world experience with AI and ML for optimization of this Sydney fish market roof. And and then like I switched to the university, like I was teaching at in Germany in Cottbus, also robotic AI fabrication related. And then I switched to the Technical University in Berlin, also like teaching in a similar chair, but more teaching work, more with students, with courses, with studios and things like that. And now like afterwards I have been like involved a lot with as a freelancer in various startups, various webinars, teachings, conferences, and now I'm having my own thing with a colleague of mine, which is called Pixelet, and we're doing actually uh, AI for the built environment, or like for in general design or engineering. So not specifically architecture related or design related or whatever, but just literally AI systems that would optimize workflows and processes, and uh, how do you get uh, AI generated stuff or digitally generated stuff in general, like much more optimized for fabrication or to be put into the real world, like breaking out of the digital, or like we're gonna talk about how to like make this choice optimization, as we would call it, how to get the most optimal out of your designs or ideas. Okay.
But just checking, we're still seeing just the first page. Is that correct?
Yeah, I'm still talking. So yeah. And now we come to the webinar actually. So what we're gonna do now actually, I'm gonna talk about the development of AI, and like how did we get from uh, historical, like how does the big story go, like that you need to be aware of, like so how did we come to actually diffusion models that we have today, because there is a big there's a quite a big high level knowledge, or like or like there's a big story you need to understand first before you dig into or interact with any of these machine learning models and systems, and like especially if you want to debug them or make your own or like get the most out of it. If you just want to be a passive user or like just maybe generate some images and that's it, or like you probably won't need it. But like if you really want to utilize it for your own needs or for your own optimizations and workflows, you need to understand the backstory behind. And I will teach it to you like, in a very, very high level without any maths and formulas and all that kind of stuff. But first of all, like, okay, yeah, we're dealing with the deep learning models. Like, I called this initially from going from text to tangible, like in 3D, because currently the whole world seems to be like focused on the text and the 3D and the 2D actually, and not too much on the 3D. And that's where I or we come in. And then like as a bonus to create we will actually learn how to animate our models and like make some cool visualizations and money shots, let's call it, for out of it. But first, before we get in to the story, I will switch to my desktop because there are some things you need to install first, which will run in the background when I start talking because it's gonna take a while. And okay, so what we'll need actually, the process goes like this. Like essentially, you can use Google Colab, which is actually this service from Google, which runs in the cloud. And it's free. It's free-ish, I would say. It has some limits. You can't use it the whole day. There are some performance limits, time limits actually, unless you buy their pro versions. So like the I don't know about you guys how strong your computers are, uh, but if you don't have a GPU, like an NVIDIA GPU available, you have a hard time, I would say. So that's why like I introduced Colab as a option, or like it's good for like getting fast results. I mean,
We
it's
only
okay.
see your desktop.
It's okay. It's okay. So
Is it correct?
yeah,
Oh,
it's okay. So so what are we gonna do now is actually I'm gonna show you uh, how to do that locally because we're gonna need the local installation preferably uh, for the second part for the animations, and we're gonna be using preferably automatic 1111. Uh, yes, you will receive the link. And the thing why I'm doing this now uh, is because you can also probably learn this in the Colab, but then you need to upload the models then because for the animation and for all of these image generations, you need to have local models installed. I mean, probably you can do that in Colab, just upload them, but that's gonna take a while because models are like very, very big and like 2, 3, 5 GB, 7. I think the latest stable diffusion is like 9 GB or something like that. So like that's gonna be like a lot uh, of storage in general. So like, so if you want to deal with these kind of things, you need a lot of storage in general. So we will be doing this actually, which is the local version. And you can do it here. Installation, automatic installation on Windows. If you have Linux, even better, or like WSL. There was a automatic installation somewhere here, which you can just run. Yeah, the WebUI zip. And you can just run the update from there. Essentially, the proper workflow would be to like download Anaconda. Like Anaconda Navigator. We download this guy. Not start coding this.
Zvonko, can you switch your chat to everyone? Otherwise, they're not.
Dependence. Yeah.
And then reshare the link.
What did you share with me? And when you do Anaconda, like, and you install it, you need to install it as a root. Wait, let me just do it and see it with you. I mean, I have everything built, but I will see it with you again. Why is this twice? I don't need it twice. And at the end of the day, you need this terminal. You need the Anaconda prompt. Why we're doing this is actually like you can also do all of this locally, like just install Python, like just go to the Python website and install it. You can like just download any Python from here, Python 3.11, okay, whatever. You can just download it and just run it from there. But the thing is like, then you're installing it directly on the system. And like, if you need to like install another library and another library, and like, it will all get in a one path. So like, they all have dependencies which are not maybe not compatible and everything. Oh yeah. Yes, Alex. Yeah. It's very, very recommended that you use either a Windows or a Mac or a Linux, because Macs are very, very fragile to these things, I would say. We will need Google. Technically, you don't, and you do need Colab. Depends on your machine, I would say. If your machine is strong enough, you can run everything locally. But for those of you with weak laptops and for faster to get things done faster, like I would recommend Colab. it's just much more easier and flexible, but it all depends on your local machine. Here, nothing counts more than your system requirements or hardware. Like there's like, it's not a very user-friendly workflow, and there's like a lot of parameters. So it's not like we just open Rhino and that's it. So, and okay, is my Anaconda done? Probably. Yes. It will complain that I already have it, but I won't go through it. Okay, next. Yeah. Menu shortcuts. Yeah, you can do this or not, because like if you register Anaconda as the default Python, you would when you go to the PowerShell, okay, not PowerPoint, PowerShell, here you would see the base. You will see Anaconda, and you have to get out of Anaconda first to access the PowerShell, or the same thing goes with CMD. So when you open CMD, like you would first see the Anaconda. And like in my case, I didn't do it because I want to access Conda either through like Anaconda prompt. So I have it directly like this. And it says base. This is how Anaconda looks like. And later, like we'll do like Conda activity, stable diffusion and stuff like that. And this will all run in the background. I'm just like telling you what the actual workflow. And here you can do environments for any package you want, for everything that you tinker with. If you want a separate environment for PyTorch, for TensorFlow, for whatever project you ever do, and it will all be containerized in this environment. So your base system will not be tampered with. And that's awesome when things get updated, or things get changed. A lot of stuff gets updated, and a lot of things breaks dependencies. Like, and there was the thing when I started dealing with these things, like that was like 2017, 18. Like in my first lab, like I was eager to update everything, like everything newest. Why not? But my professor then was like, no, don't touch it. And later I found out why, because with each new dependencies, each new versions, like they need to be like ultra clean and like certified that will work with every hardware, every other dependency that you would later on use. I was using OpenCV there then for computer vision, and like one of the updates broke some of the things we were working, some of the other things we were working with then. But that's another story. So always use environments. And that, and the thing is, the next thing you need to download actually is like the models, which is you go to Civit AI, and you would find like a ton of models here. You have for any occasion. Character, style, celebrities, base models, clothing, buildings, whatever, whatnot. And you can choose any model from here. Usually, like, and you need to like, you can choose, okay, these are all stable diffusion models, so you can choose any of them. I just like, I really like the, what was it called? Dream Sheeper. I really like the Dream Sheeper. It's very cool. So, and there also, you can just go and like download. And there's like a ton of versions for inpainting, for diffusion, for whatever, whatnot. These are all the versions you can find of this model. And the thing I like about this website is like when you open up this picture, you see the prompts and you can actually learn a bit of prompt engineering from them, how these images were created. Or you just like go to Hugging Face. Hugging Face is the thing for building models. And you go to the models and you can, from here, you can just download Stable Diffusion XL. Which is the latest Stable Diffusion. You need the Safe Tensors versions. These are the model images. But you need the base and you need the refiner as well. So Stable Diffusion, the one comes in 2 packages. The previous ones come in only one, but all of these that you would see actually also on Civet, they all come mostly as safe tensors. Yeah, safe tensors. We'll talk later about how to integrate them, but for now, like until when I begin the talk, I want you to like put all this stuff running because it will take a while. Because like in the Anaconda, okay, I'm not gonna install it right now because I already have it. Because it will take a while to install and you need to do PyTorch and like all of these heavy dependencies that like, I mean, probably you can also do that, all of this on the Google Colab, but it will still need to download even there and like get some models and you need to upload some models or fine. It's mostly the same thing, but like you're not using your own hardware, which kind of the thing with Colab is like you can't use it all the time. I mean, you have to have it on, like somebody has to be there because like if I leave this right now, like it will, I mean, now I'm not connected. It doesn't care, but if I was connected and all of that thing, it would bother me like, are you here? Please confirm that you're here, no activity from your computer and stuff like that, unless you're a pro, like a paid customer. So I would still recommend to do everything locally because you know it's there, you can touch it. If you break it, you can get it back. You can leave it running for forever, and that's it. Because these models, if you want good like outputs or like perfect details or whatnot, like depends on your computer or like, but you will need some big training times. That also goes for 3D. For 3D especially. Okay, so is everybody clear up to now? Okay, so okay, so let me start off. So, what is an optimal design in general? What do you think of when somebody tells you, okay, this has been optimized, has been AI generated, algorithmically made, and all of that stuff? Is that like, do you think first on the process or the design, or or something in between? Like in general, like the first time uh, I was encountered with this is like actually, yeah, when I started professionally working, when I got this task uh, for then it was the Sydney fish market. I made it. I have had such problems in a couple of other studios before, but that was the most like um, important one. And the thing is, like, okay, they tell you to, okay, now uh, design this roof, but make it like the most optimal as possible, that like later in all of the uh, following phases, when the actual structure comes and the actual costs come, when the invoices, let's say, come, that it would be as optimized as possible. So like you would have this kind of initial design of this truss, and it looks as it's so. It's a space frame that weighs so and so tons and weighs that much euros. But then, like, you get all of the parameters, you get all of the objectives that needs to be like constrained or like thought through or like optimized, and you run through all these calculations and such, or you get to this frame that actually you can be saving a lot more actually than you have already. uh, and this is like actually uh, very, very useful. I mean, this is for now, we're not even touching any of the ML or AI story so far. Like, not right now, we're just talking about pure mathematics and calculations and statistics. And like, so that you have like right now a single objective. Okay, you have one goal, the fitness. Like, okay, make it cheaper. Like, okay, you made it from 750K to like 340. Okay, that's only the single objective. Like, because there's like multiple types of these kind of optimizations. You have like a single objective and like a multi-objective. I mean, uh, some of you are familiar with this, like if you have been doing Galapagos or Octopus and things like this in Grasshopper. And these things are also like algorithms that aid, uh, let's call them machine learning processes. And yeah, we said like we have multiple fitnesses and inputs in multi-objective. Yeah, so that we have like only a single result or like a choice of results, because you can't choose like in multi-objective. You have to choose. Uh, the human has to like make the final choice. So like here there is this whole area of choice optimization and this kind of statistical modeling and pure mathematics and computer science, like for now. So like, and that looks like this, right? You have all of these roofs or roof shapes or that like are in this kind of X and Y field. In ML, we call this the latent space. Right now, it's just a field. And we have all these features here, like all of these roofs, let's call it, which have like X and Y values, these kind of points in this kind of field. And the X and Y can be like price to performance, price and whatever you name the X and Y with. That's why it's called goal1 and goal2. And like this curve is called the Pareto run. So the everything closest to this line has the kind of optimal for one of these parameters. So, and this is like very basic. Like this is only mathematics and computer science and statistics. We have no machine learning yet, but this is a very important part of algorithmic knowledge that's later transcended into machine learning. And like in 3D, it looks like this. You have the latent space like in three dimensions. So like each of these spatial points is one of these roofs with two dimensions or like 3 dimensions here, 3 values for columns, what's it here, maximum distance and deflection. So the XYZ coordinates of all of these points represent any of these variables or parameters from each of these. Let's call them panels. Why not? But then, okay, then what is machine learning? Okay, because like for up till now, like kind of uh, the human had all of the strings kind of the data was there, you just had to run it through the formula and that's it. Everything is kind of very straightforward and that's it. But then like machine learning as the definition says, like it's a kind of a subset of AI to perform this kind of specific tasks or find solution or to problems. I would add here also predictions, or like predicting the state that's gonna be or should be, or in which cases what should be like according to your wishes, of course. So like in this case, like here we have everything laid out open on the table, but how would this look like if we add more variables that are not known, like how they would look like in some other case? So that's where the generative AI part comes, the generative segment actually. So like we have supervised and unsupervised actually. Like as we said, like only based on the input and output, where we kind of expect what we can get. Like we already know what are all of our options. And unsupervised, we have only the inputs. So like we just feed in the data and it figures out what it needs to do. And here we have the regressions, which are we're gonna be talking about the first, like to predict quantity, and then classification, like just labeling data, or like recognizing stuff. And then we have clustering, yeah, which can be kind of supervised and unsupervised. Also neural nets. Neural nets are like a very specific category because they can be also in both. Depends on the inputs and the goal you're aiming with them. I'll tell you later because there will be also like a very crucial part later. And then we have like a very special category which is reinforcement. We're not gonna touch on that today because it's a very, very complex thing. And it's like training based on rewards and punishments for the model to achieve. And that's where you literally you've seen those videos where they teach algorithms like to play games, or like there was a algorithm I saw recently that they make that can play Super Mario on its own, or like Tetris or something like that. Oh yeah, there was a reinforcement learning thing I saw that learned how to play table tennis or tennis out of without like they taught a robot, actually a physical robot uh, that could actually play table tennis with you, like which is uh, uh, trained on like a lot of like videos. They just scrape them from the net, and then they just train the robot with reinforcement learning, just to, like uh, being able to play with you. But enough of that. Let's go on to our thing. Let's say now, okay, we we move on with our story with the panels. Let's say, okay, we need to choose. Okay, we did all the panels, we did the roof. Now, new project. It was awesome. Your skills rock. But now we need you to find a new plot. We have another project. We need you to find a new plot. Where is the most optimal place in this town to build this kind of structure? Okay, you you browse to whatever network you have, internet, whatever, and then you'll find these plots, all of these dots. And then, okay, you make this price area chart, but now we need to teach the computer how to select one of these. And because the computer is being blind, literally, every time you need to train a model, you need to understand, you need to feed him like a blind baby, literally. Like everybody is laughing about this, but it's true because so like you need to give him everything. Like, right now, he doesn't know any, so he will just make a random guess. He would need to make a random line because the thing about classification or like mm, traditional machine learning methods is how to fit a line through a set of points to split them in the best way possible in the given context, of course. And the the computer being blind, he will just start drawing random lines. And it might be like this, might be like this. I don't know. Is that optimal? We don't know. And the first thing we're gonna talk about, the first model we're gonna be talking about is linear regression, actually. And the way how linear regression works is that this guy needs to be moved around like this, right? So it would find the most optimal distance from all of these points to the line. So, okay, these ones are too far, this is too close. So we need like a lot of iterations, a lot of trials to make them, and the point or the points depends on what your criteria is, that are closest to the line is the more favorable choice for these two parameters of area and price. And that's this wiggling of the line is called the gradient descent. And this term you'll hear quite often. And you'll see later why you'll hear it quite often. It's this descending of all values, like this kind of optimization, let's call it, of all values. And that's called, and the way that that's done, actually, it's like it measures distance from here, from here, from here, from here, from all of these points to this line. But then this line has two sides, positive side and a negative side. So it has to be squared. So there will be no negatives. And that's the least, that's called the least squares method. You will hear that as well. And I'm telling you this out of a data science approach, so you would get lost with the terms later on. Okay, but now we need something more specific. Let's say, okay, we need to split our line, but right now we only get like a couple of like solutions. This doesn't fit like a lot of cases. You know, like here, everything is like here, like everything is staged by us, kind of. What if we don't know a thing? We just like scrape all of these plots from the internet or panels. It can be anything you want. And then we just define, we make like a side note somewhere that like, okay, my ideal panel, let's call it a panel, is, if it's a big panel, it should be like this and this meters high or wide. If it's a small panel, it should be this proportion, these parameters. So like we make these kind of classes in programming, that they're called classes, where we define the actual description of what our criteria is for each thing. Like in this case, maybe we call it the most simply the big panel, the small panel, medium panel, or like, I don't know, some great panel, whatever specific context-related thing you have. And then we need to train the algorithm to find in this sea of unknown things that we have in front of us, how to like classify or like find the best things that suit our needs. And of course, it's still supervised kind of learning. That's why it's called unsupervised. And of course, we start with a line. This is the line. Maybe it splits it like this. It's on half. Why not? And the thing is, like, this is the basic formula of a line. And if we get the XY coordinates of each of these points and replace it with here, we would get the coefficient. We'll get this kind of probability, let's call it. And if we set a threshold, we can measure like how close we are to our threshold and how nice it is for us in that sense. So this is called the perceptron. Actually, this is the most basic neural network, or the predecessor to the modern neural networks we know. And it's very, very old. I think it's from the 1915s or something, and it's like a mathematical model or something. And that's here we introduce the binary choice. So like with this threshold, we said, like you just say, okay, it is or it's not, like fitting to our needs. And that's like very, very rough. It's like very, is it black or white kind of classification? But for today's world, that doesn't really count, or doesn't, because like in today's world, we have like much more sophisticated thing to classify, like for example, spam emails. In that case, like, yeah, you can imagine this field as like a lot of spam email, or a lot of emails with a lot of that you train it on a lot of different contexts, and like filter out from words and do all this kind of semantic detection, and like but you need something more refined. You need to add this kind of probability sense, this kind of probability coefficient, actually. And that's where the kind of uh, next evolution of this would be, was or is, logistic regression. And logistic regression is the actual kind of forefront to neural networks. I mean, I'm building the story up, everything towards the current state of neural networks and models and all these kind of things. And here we have the loss function. Here we introduced a loss function. So like from all of these, you have like an error metric as with the threshold, but it's a probability, like it's a rate from 0 to 1. So like this guy is 0.25% to be a big panel, but like it's more likely to be a small panel. All of these like reparametrized version, if you know, if you have used Grasshopper, it's called like in this reparametrized domain, or normalized domain, it's called in some cases. And then the most famous function for that is called the sigmoid. We'll deal with the sigmoid quite a lot later. And the moving of this line, I forgot to tell you, is called the learning rate. So how fast this line moves around this field. And if it moves too fast, you would learn too quickly, but you are much more prone to errors. But if you learn too slow, you might be stuck, and then your model will be uh, not even seeing, or like can get passed by very, very ordinary problems, or very, very basic solutions that you would need a model to solve. And this is done like in a lot of epochs. That's kind of let's call them the iterations. And then like, okay, we have this thing, but it's split on two in this case by this line. What if what happens if you want even more control? But that's in this case we have these two clusters, and these are severely like more to one side than to the other, like these, let's call them panels again, are too wide but not too tall, and these guys are uh, the other side, so on the other spectrum. So in this case, this logistic regression function is not very refined. You can't very refine your solutions too much. There is some probabilities, as we said, but it's not very refined. So we need to like add more lines here. Like in this case, we have like only a pizza cut, like with like one knife, and now we need actually some samurai sword ninja that would like actually cut this thing very fast. And maybe it should look more like this. There actually, in from a data scientist point of view, there are also polynomial linear regressions and like all of these things, but we don't have the time now to explain all of this, all of that actually. So ours, in this case, like our solutions would most likely look like this, maybe a bit chopped up, maybe with from different epochs or from different uh, iterations and like different curves, actually different functions. And this is how modern neural networks are actually constructed. Like at the end of the day, I have this kind of clustering from that has been chopped up with a lot of lines, a lot of different lines, polylines, curves, so that we have this kind of a bit more refined classification. And this is kind of the beginnings of the modern, let's call them neural networks. And when I'm talking about moderns, I think it's like 50 years ago or at least 20, 30. Maybe not for deep learning, but like for these classical things, yes, probably. And then, but I have to mention this works best in the classical sense with labeled data. We'll talk later about how to what to use or how stuff works for unlabeled data, for because that's the hot topic now. Let's call it doing stuff that the algorithm has no clue about beforehand. So everybody up good up till now? Any questions, doubts, remarks? You might be confused now because I'm telling you the a story that takes like at least 3 months of data science to properly dig deep into with all the uh, formulas and maths and how and why and code. But it's I would be glad if I know better you understand the story at the very very high level for now. Good. Okay. So for now, we're talking about some parameters, these parameters or features or dimensions that go into this classifier. It's a black box, let's call it, and then you have some outputs. Depends on how much outputs we specified and stuff like that. And at the end, we get this kind of score, which is the error metric, as it was with logistic regression and the perceptron and stuff like that. We have some score at the end that tells us, okay, this output is so much true to the original, or it behaves the predicted way that we wanted to behave. And modern neural network, or looks like this. So we have a lot of inputs, which are these p's, the parameters, and they go through a neuron. This is the actual neural network, which is called the hidden layer, and they go through an output. We receive an output, and all of these, the thing is, like, all of these parameters, this is a number, it gets multiplied by this activation function, which is the sigmoid. That also happens it's automatic 1111. Just search for. Wait, let me just see it. It's this one. I mean, if you go to the main page, not this page, you have a README, and you can choose your GPU. By default, I just do the NVIDIA, but there's also, I think, instructions for Macs and Silicon and stuff like that. But anyway. Anyway. We have the parameters, okay, they get multiplied by this function and they come out, basically. But there's a bit more finesse to that, because we have also weights and biases. And like the weights mean, like, for each of these parameters, how strong they should influence the overall output from this whole net. So like, maybe if these three are like with height and something else, maybe you say, okay, I want a solution that's more inclined to the width but less inclined to the height, or whatever it is. And the biases are kind of like regulating the equation. So like, if you look at the sigmoid, if you look at you know how the sigmoid looks kind of like the sine, if you know how the sine function looks like. So the bias actually regulates this function, like to keep it like in an appropriate, let's call it, values. So like it just shifts it left or right, more to the left or more to the right on the graph. And then we get the output data. But that's only once. Like forward propagation means actually we just do this once. Only one way. All of these get together, like they get activated, they work together, and that's okay. But we don't usually want that output because like that might not be the optimal choice. That's not uh, optimized at all, I would say. So what we do actually when we train the model, actually, we actually employ the backpropagation. And we'll get that in a bit. So this is only one layer, but we can have like tons of layers here. And the more layers you have, like the more computation time, that's what there will be more refined the solution may be. That all depends on the context, on what data you fit in here. Depends on the complexity of the problem, how much time or like resources does it need to like mitigate to solve that problem. And that's where we come to the backpropagation. Like here comes the training part actually, where it sends them back and forth. So this kind of dynamic adjustment of weights and biases. So in order to like make everything harmonious and optimized, and like in which like if you have used Galapagos and octopus and stuff and things like that, like that's like when you optimize the seed value, right? You need to like go through a lot of uh, combinations or fitness values um, by by going through these sliders and pulling them like left and right and up and stuff like that. So like you'll get to the best solution. So backpropagation works similarly. Like you just send this activation function, let's call it, back and forth until you reduce the error. Because at the end of the day, as we said, you get an error. You get this kind of loss value. So like and that's the whole um, point of deep learning, let's call it. There are a bit more finesses to this, but I would also say that like in between this uh, uh, this backpropagation is also run by gradient descent. Like I told you, we're gonna uh, run into this turn a lot, and like in between all of these steps, these kind of optimization steps runs gradient descent. Yes, you can. I mean, you can always retrain. That's actually, you touched upon a very good point, which is like very uh, uh, key, uh, not a mishap, but a key challenge of data scientists and uh, machine learning engineers and stuff like that, which is this kind of hyperparameter tuning. Uh, because like with each retraining, you might get like uh, less error or more error. We don't know. Depends on how you set the initial parameters, which are uh, these kind of learning rates, uh, epochs, and depends on. There's also like um, a very. I need to tell you now about actually the difference between a parameter and a hyperparameter. Does anybody know the difference? Because you you would hear this also quite often. Like like a parameter is a thing a human sets, uh, or not a human sets, like that is set by default, like, and it can't be changed. And the hyperparameter is a thing set by the human, and like that can be changed. Like, and that's what the model actually tries to optimize. It tries to optimize the hyperparameters. And that's in almost any model. That the same, you have been doing that in a very graphical way and a very, let's call it child-friendly way in Grasshopper as well. Then you have all these kind of sliders, like fitness objective and fitness function and all of these kind of things. And but then, yeah, now we go into the deep learning, and we the first problem of deep learning actually until uh, quite a while ago was the vanishing gradient, because like I told you, like, we imply gradient descent for each of these steps, but then like when you have this line, like we did, like where was it, like maybe this line, or like I like the one from here better. When this line v goes too much, you may like this goes on too much, it will become at some point too flat, or not too flat, but like it wouldn't have a lot of values to optimize, or like to and that would be kind of inaccurate. Uh, it will get you will get very, very inaccurate results, and some models would not even stop training until then. And why is this a problem? You can imagine this problem as uh, like you're rolling a ball like up a hill, and you get to the end and there's like a plateau, and like it's super easy, then it just goes smooth and there's nothing. And this was a problem uh, when using the sigmoid function. Now there are some other things that kind of like minimize this problem, but like after a certain point, the model stops training. Not stops like stops in captions. It stops learning, and that means it. And then we come to the point of overfitting your model or overtraining. There was an anecdote actually when I was doing the data science academy that like if you train your model too much, it's like when you give it to face a new problem or like a more modern problem or a current model problem, it would not know how to deal with it, or it will deal with it very, very slowly because like run diffusion. What is that? Hmm. Yeah, but the thing is, in this sense, for these kind of things, for this run diffusion, I don't know if you can see my chat, but I just had I just read this message for run diffusion. Somebody uh, uh, posted, and the thing is, like, I prefer to do it locally because uh, you'd have the models, and for animation, you would need like a lot of time. And plus, we're not just generating images in this sense. So in the most optimal sense, case, you will just rent on AWS or Google Cloud or whatever, so that you would have a proper Ubuntu there and run everything on the cloud. Okay. Okay. But the thing is with now the thing with backpropagation is like it's very, very time consuming and inaccurate for high dimensional or deep learning, because like everything is high dimensional uh, when it has like a lot of inputs. Like all of these inputs are the dimensions, all these parameters are the dimensions. Like in, I mean, I'm just telling you toy examples, like with panels which have like 3, 4, 5 parameters or dimensions at most, but like uh, models for generating images or 3D or like very, very, very uh, deep data or like complex data have like millions of parameters, millions. Like I think the latest stable diffusion parameter model has like 10 billion parameters or something like that. So, so that's like very, very time consuming, and like that's why it takes like a lot of time to train. And that's why we have this we coming to another model that was also kind of relatively new, which is called the restricted Boltzmann machine, which actually all the inputs are not connected to each other. Like it's only connected to two inputs. So it's kind of like a feed forward network. And it's the cool thing about it, it's extracting features from data. So it works without the labeling. Uh, Okay. In stable diffusion. Now, in stable diffusion or like in diffusion models in general, you have parameters like CFG or like denoising and like also width and height and stuff like that. But like you'll see it later. There's like a lot of technical parameters in diffusion models, but the most important are like CFG and denoising. Anyhow, this guy works without labeled data. And that's where we come to the autoencoders, which actually encode data. And so it takes the data and like kind of dummifies it. That's why it's called the dimensionality reduction. And like on that simplified thing, it learns the patterns. So then it can like actually reconstruct it. And this looks like this, like the whole network, and it's called the deep belief network, consisting on multiple these RBMs or Boltzmann machines. So like you have the encoding part, which kind of from 4 outputs, dimensionality reduction into 3, and then it tries to reconstruct it in the hidden network, and then they output it, and that's how it trains. Here it just comes out as latent space or latent numbers, like that are gonna be stored in the model. And yes, we can also make it deep when we have like a big enough network. And as a picture that this looks like, so you have a mushroom and you want to teach the algorithm that, okay, a mushroom looks like so. So it encodes it, makes it into compressed data, and then this is the learned representation. When you ask for a mushroom, like you would get this. And the most famous, I guess, of these are the earliest that I know of actually uh, is GANs, actually, the generative adversarial networks. GANs were before the diffusion model hype. GANs were the kings, let's call it, or the go-to thing for this kind of stuff. So you have like the data set of real images, which is kind of the samples, and we have the generator, which makes fake samples actually. And then there is like a discriminator part that actually tells the model, okay, is this real or this fake? And then we get, as with all neural networks, we have a loss value. And the cool thing about GANs is like it just like works on the fly, but it takes a long time to train and a long time to and it's quite hard to like approximate or get the results straight or get some nice results. I mean, from the image sense, like I'm talking about the visual stuff right now. It's kind of like a bit of a hassle to train them right or get meaningful results that don't look like some meshed up kid drawing, whatever. I mean, And I think the most famous here was the Deep Dream. Like, I think from an architectural perspective, they have been doing this with Coop Himmelblau, like this Deep Himmelblau and stuff like that, where they did like these deep dream representations of like visions of, I don't know, Zaha Hadid architecture and stuff like that. And there's a lot of GANs around still. I think also like this was the if you're now familiar with ControlNet, which is like kind of a new thing, this was before as the GAN version of it. It's called Pix to Pix. Actually, you draw a thing and then like you give it to the GAN. It has been trained on like a lot of pictures, and it's like, okay, this guy should look like this, but there's like also, or this cat. So, but there's also like fails and not fails. Maybe so. And this is like quite old. Like this is like at least 5 years old, maybe. Yeah. And also we have like the rise of maps, like maps being used as like training data, like all of these labels from computer vision, like or various depth maps from aerial viewings, or and you can just say, okay, when I label all of these colors, that this is a window, this belongs to a terrace, to a fence, to a balcony, to a whatever, then it can like dream out, if I can say it like that, like how this facade would look like based on like trained data. Or this day to night. And in Rhino, like the first one that I saw, that what it was called cycle jam, that you get this Rhino viewport and then say I want it in, I don't know, a pay-per-view or like whatever your condition is, and you can get like a image like dreamed out by again transformed. This was like a long time ago, like 2017. And now we come to our thing. Is everything clear up till now? Or at least do you get the basic logic of the story? I have this question and like that while training the model in every step of the network, we're reducing one parameter. Not really, because like your dimensionality reduction works so that it just like uh, groups or like uh, tries to like group all of these together, because like at the end of the day you would still need to like uh, get all the parameters out, right? I mean, it's not like you're just like kicking them out, right? But it makes just like a simplified representation of it, so it can learn on. Yeah. And now we come to our thing. So the thing like how diffusion. First, actually, we need to talk about how. I mean, actually, I told you why GANs don't work. I mean, GANs take like a lot of time to make. For good results or for like acceptable results, like they take like a lot of time to train, and the results are like very very uh, hard to interpret. I mean, depends on the context and what you expect for it, but for visual purposes, it takes like a lot of time to train. But on the other hand, like diffusion models, like don't have this advers. It's called the adversarial step, like this adversarial training, because like they just take an image. In this case, it's an image. It can be used for anything. Like uh, diffusion models have been also used for like denoising and like classification and like I don't actually I'm not sure about classification, but denoising for sure. Or and and also 3D generation and stuff like that. So obviously, and what it does is actually takes the image and it breaks it down, literally. It turns it into noise, and from that noise, from that Gaussian noise, uh, it it um, it tries to get it back, like it tries to like resemble the pieces back. So like that's why here you have the forward diffusion, where it just turns it into noise, and then there is the reverse diffusion, that where it tries to learn how to represent the image back. And that's how diffusion models work for images. I mean, this doesn't, this is not only applied to stable diffusion. Don't look at the stable here. Like this goes for any diffusion. Like there's like also like disco diffusion and mid-journey, of course, and like dolly and whatnot. And the thing why diffusion models are powerful is just because of this um, easy like and very very easy to train, like but for they take a lot of computational power, like a lot. So I how how fast they operate or how fast they train, uh, it only depends on your requirements, literally. That's why I you need like a very beefy computer or like a cloud if you want some very high quality results, especially for images and models and stuff like that, or uh, you need a very, very beefy workstation, because like only the models themselves are very huge, and plus everything gets loaded in the memory beforehand. So I had like struggles with my own computer, that like I couldn't even load the new stable diffusion models because I didn't even have enough RAM to hold it. I mean, not just VRAM, like also physical RAM, because sometimes they're shared, and let alone then process it and like run PyTorch on it and whatnot. So if possible, run it on a cloud. But then like for our purposes, that's not really nice, because like we don't have the flexibility then to do what we want. Okay. But then we have like the pix-to-pix version, let's call it, uh, of diffusion models, which is called like control net. And the way control net works is that like it's kind of like a neural network addition. It comes in the diffusion model, like it operates with the diffusion model actually, uh, and it comes on top, like kind of like another layer in this activation. And the thing with control net is like it can like enhance uh, what this image is. Like, okay, we have this image, it has been learned, like this is the prompt, like it's coupled by an LLM. Yeah, that's another story. With uh, stable diffusion things are like these models are coupled mostly with an LLM, like a large language model, which gives up the labels, obviously. And and we have all these maps the control net is trained upon. And here, if you can read it, like you can, this control net was trained on line maps. Yeah, so if you feed him this image, it will spit out the line map of it. But you can also do it the other way around. You can just give this to a control net uh, in conjunction with your chosen model, because it can be any model, any SV downloaded from Civit, whatever, and then it will give you like a representation of what he thinks this is. So you have all these variants which were made either from a single prompt or with no prompt at all, just with this image. And that looks like this, another variant, or like this with segmentation maps. So these are some control net parameters you can see here actually. Are, are you talking about generating the line map like from an image, or like using a line map of your own to generate something? Yeah, like you can do it both ways, actually. You can use the control net to generate a line map from an image. That, I mean, this process is very stackable. Like you can uh, generate first an image from a prompt, then generate the line map from the control net, and then send it back. Like generate something new, totally new from that line map. So like this process is like you can uh, put it around and around and around as much as you like. Does that answer your question? Okay. And the latest, yeah, you can stack as I said, like you can like stack a lot of control nets. Here you can like as you can do with the network neurons actually in the hidden layer, you can stack a lot of control nets together. So you would have uh, not just predefined, okay, I'm just doing the line and that's it. So you can make a lot of uh, the line and the segmentation and the whatever you find, and then make like weights. You remember the weights and the biases of each control net. So like to get something very, very crazy, unique, or that would be like uh, something un very, very unique. And like the thing that was most famous uh, for that was these QR codes, actually. Like some people were doing these kind of QR codes. These are like just multiple control nets stacked together. Like you have a because what's a QR code? Like it just like squares, lines filled on a white image, and you can stack that with any image, like and adjust the weights, adjust the biases, make it look nice enough or readable enough, and you can actually scan it and use it, and you have a QR code with an artwork made by controller. Okay. Is everybody, how's your automatic going? Or all this Anaconda? Okay, but we're not gonna use it yet. I'm gonna stop my screen share. I need to, I didn't mean to stop the screen share. Actually wanted just to like stop the presentation. Now we're back to the beautiful lighthouse. Now we're gonna go into the 3D part, and we need this checkpoint. I mean, we're gonna be doing this. I will send you this Jupyter notebook. Oh yeah, important thing. Like, how much of you have worked with Jupyter notebooks? Because if you're doing data science and like machine learning, this will be like one of the top things. Oh yeah. Seconds. File. Yeah, we're gonna open it right now. That's why I asked uh, how much, how many of you have worked with Jupyter notebooks. Jupyter notebooks are very, very simple, actually. It's an interface for Python. Instead of like opening up Visual Studio Code and like seeing a raw Python file that you have to like only you don't see what you are debugging, right? So like in Jupyter notebooks, you can just like debug every line and see what happens when you make changes to each line of the code. It works in Visual Studio Code as well as like in Colab. So what you do is actually open up Colab. In the Python IDE, no, you need Visual Studio Code. In Visual Studio Code, like the Colab way is to like just when you open up Colab and you go upload notebook here, you can just like put your Jupyter notebook here and it will like open up this. So you can tinker with it. Or in Visual Studio Code, that you need to set up an environment for Visual Studio Code first. So for this step, like for the sake of speed, I would recommend using Colab. It's much faster because in Visual Studio Code, you first need to set up this environment. And that's gonna take a while. And in Colab, everything's like already done. The thing like what it did actually, like why I told you I'm telling you that you need to set up the environment here is the same as automatic 1111 makes an environment. So like when I go open up something, here detecting kernels, and you have all the environments you did with Anaconda here. So if you do this locally, you need to like open up Anaconda prompt, like create a new environment. There's like a Conda cheat sheet. Fun, find it. So you need to create a new environment with the specified Python and stuff like that. Then install TensorFlow, then like install all the requirements. It's a bit more manual work. And the same thing is done here, actually. Because it just like clones the repository that we need, and then it installs it. But then all of these things, Colab has PyTorch and all of these default libraries like installed by default on each new instance. So we don't have to like worry about that. And now I'm just like, not yet, wait. Is everybody ready? I mean, there were some, I've tried also to like run Colab, like, but locally, but you don't need actually because it's a Jupyter notebook. Yes, we just need to upload the notebook to Colab. It's just easier for demonstration purposes and for the purposes of this workshop. It's just easier for this part. For automatic, not really. And I just click on connect. Okay. Just this. This. Actually, this can be commented out. Control KC to comment out stuff, or just make a hashtag in front. And then there's the ugly part about Colab. In most cases, you have to do everything from the start, unless you connect your Google Drive to it. But then, like, if you're working with like very, very big models, it's gonna consume a lot of your Google Drive. And that's like a kind of a pain. This thing will take a while because this one actually downloads the models. In the meantime, like, what do you want to generate? What would you say we should generate? We can make a poll or whatever. Thing with the code is like, okay, you install stuff, that's okay. You need to check like if CUDA is available, because otherwise, if CUDA is not available, you'll have a hard time. You'll have like pretty much a lot of waiting, a lot. And then, okay, you download the base model. You need also the upsample model. And like the checkpoint, this kind of, as we saw at Civit, the tensors. And then it gets the base model. But then we need the sampler, because these are point clouds. We're downloading like a point cloud model. And this, like, yeah, you see now Colab is kind of, and these things you'll get all the time. And like, yeah, we have the diffusion model here. The base model is what we set here. The checkpoints, actually. This is the resolution. This could not be changed. I tried so many times to change this, but it just like hard coded to work in that resolution. And we have 3 like color channels, RGB, and this is the CFG. What I told you about the CFG, the guidance scale, actually, this is the thing. So like what CFG means is like how much how much the prompt or the output actually would be true to the prompt itself as like a linguistically true, or how much it would have freedom to like experiment. And like right now it's set on 3. For images, I recommend to like set it on 7. Here it was like 3, so it's like sticking quite closely to the prompt. In this case, you can't change the base model. It's a pre-trained model. For 3D, there is no such thing as a CVIT for 3D yet. So because the base thing here now it's set. But it's the minimum and maximum value, like for the guidance scale. So it's a domain from 3 to 0. It's an interval. This do you know what this is in general? It's a NumPy array. It's a list of numbers. So it's a minimum and maximum. So what would you like to train? We can train anything right now. What would you like your output to be? We can also make it something completely wacky. We can make a monkey chair. Why not? Monkey chair. Who's up for a monkey chair? 3D printed monkey chair. Why not? But then it's not gonna be all right. And okay, This goes in, and now it starts training. Because so far we only loaded the model. Like we only loaded the parameters, we just downloaded it, blah blah blah, all that stuff, and now the actual training begins. And this is why I like Colab, because this runs relatively fast. And here you see there are like a lot of uh, parameters. You can do the batch size. Actually, the batch size is one. The batch size is actually quite important because like it uh, tells you how much samples go through each of the epochs. Let's call it so. So it's only learning one by one now. It's not learning on like 5 at once. And like it's kind of like the learning rate I showed you like in logistic regression or something like in in this case it's called the batch size. Yes, like we're training now. Like what happens is like okay, uh, we because this diffusion model is coupled with an LLM, as I told you. Like when you input the prompt, in this case, the 3D printed monkey chair, it needs to resemble uh, what's a 3D printed monkey chair, first of all, and then it will spit out the point clouds relevant to that. So we will get a 3D model, don't worry. It's done. It's done. Okay, it's a chair, but I don't know if it looks like a monkey, maybe. And like when we reset, maybe, I don't know, from this side, this might look a bit monkey-ish. What do you guys think? Yeah, it's the Jupyter notebook I shared. Like scroll in this chat, and there is a this IPNB file. Jupyter notebooks are called with the extensions IP and B. Okay. Yeah, and you will get like a lot of I don't know, for humans bizarre uh, answers or results. So it's a lot of fun, I would say, to tinker what can you get out of it. But does everybody have their monkey chair or whatever? Like you can also just save it when you run all these and you go here in the side, you get the CSV and the JSON file, which is very important. And these we will need in Rhino. What should we generate next? What's everybody's status? If somebody knows how to write more complex prompts than me, can freely paste something. Do you have an idea? Give me some topics. What would you like to generate? In the meantime, we can see what happens if we put this to 7, like pump up the guidance scale, so it wouldn't be too similar to the prompt. Like give it more freedom, and we can just like reset again, and this will train once again. Yeah, actually, the 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 thing is like it sucks with detail. I mean, so far as I have used it, it's much better for something that's like solid, like in the sense of like this industrial design stuff, let's call it. So like if you input, maybe it works as maybe for cars and planes and like these kind of things might work, but I don't imagine making it a proper castle. I don't know. Or it's gonna be like those sandbox castles like that children put sand in, stuff like that to play on the beach. So I don't expect any wow intricacy right in this moment from this. Yeah. It's the question how to increase the resolution of the point cloud. And the thing is, like, I have been struggling with that myself because, like, this is a pre-trained model and the resolution has been set already. And like, in order to like make a new model, like you need to find a lot of point clouds in higher resolution and retrain it with that resolution. There is, uh, and that's a hassle. Never mind. It's also a question being is it always doing 130 iterations? I think that depends on when does it converge, because like there is no obvious epoch input. I think that matters like uh, when the model converges like to a solution in this case, because if you where was it? If you get the batch size more up or like tinker with any of these except for the number of points and stuff like that, the you will get different, I think, iterations. And also like don't ever change the resolution. That's also a problem, like also in 2D stable diffusion and like 2D, like if you notice like most of the models on Civit uh, or any model, uh, there is a thing. How do I get? Up? And up here, you open up this guy, you will see that the base model is stable diffusion 1.5, and stable diffusion 1.5 was trained on images which were like 500 by 500. So it best works best on images which are are 500 by 500 because the base images were in this resolution, and the new stable diffusion was trained on 1024, so like, it's double the resolution. So its native resolution it's much higher. So if you do smaller images with it, it's not gonna perform its best. And the the same thing is here. if you try to change any of these parameters, you will get either an error or a very shitty result. When I pumped up the guidance to 7, now it looks more cherry. Not anyhow. I see you need a bit more explanation of the process. Like, yeah, like as one, maybe the one listener, like anonymous attendee, like asked, like yeah, in the sense, yeah, like a trained LLM like interprets, like, because like the way how you start this off is like you have like a ton of point clouds which are labeled, like they mostly come in this point cloud uh, format, or a CSV, like, or a JSON. The point cloud doesn't care, and that is being assigned a label. Like, this is how all of these points in these coordinates like represent a car, like, or I don't know, a cheese block, whatever you might think. And when you come to the interpretation part, when you mix and match like the word, it might spit out like unconventional results, or not. That depends on the weights and the biases, or the guidance scale in this sense. So I think of the guidance scale kind of like these weights and biases, as I told you, like, because here, if you push it up, where was my, if you push this up, like, it will be not so biased. It might make something totally abstract, imaginary, but still kind of depends on the complexity of your prompt. I mean, if you just put in a chair and this is high or low, pretty much it's gonna be the same input, because the chair as a word, or as a token, as it's called in NLP, it's called a token, and it doesn't have any complexity. It's not like a mid-century chair designed by somebody in the year of 18 blah blah blah, something ultra ultra descriptive, so it doesn't have too much room to experiment, and so it all comes to the complexity of the prompt and the guidance scale. And then we're trained the part when the human comes, actually, we're launching this process. We're training actually uh, our input, our prompts. We're training the network to act only on this prompt. But we're actually in this huge latent space. Like when you access the model, you have this huge latent space of images or points or uh, data or however the model is structured, and you with your prompt, with your unique prompt, actually you're trying to get a piece of this latent space that would like uh, most likely like represent your prompt, like or like to to make like a cocktail of uh, from pieces from the this latent space that would suit your prompt. Does this kind of answer your question? All right. Okay. Shall we train more? Does anybody want to see something new? Somebody asked that where do point clouds come from? The point clouds, like actually, like the model was trained on point clouds, so the model is kind of point clouds. Like the model is this kind of latent space, as we saw, like with the graph and like uh, all these things with the panels and stuff like that, which are each point clouds labeled. So like the model has been is all point clouds, and like it has been pre-trained, made available for us, and all that. We just downloaded it, we pulled it from GitHub, and we installed it through Colab. And, and otherwise, we'll have to do that manually with installing all the dependencies, building the environment, and all of that. Does it answer your question? And we will I mean, I already did show you kind of briefly how to download it, but I will show it to you again. Like when you go, like after you get your view here, and you have these things to save the point cloud. So it first makes a point cloud plot, actually, and then that point cloud plot, because it's just like x and y, x, y, z values. It's a data frame, like it's called a data frame or a CSV file, if you want to call it, like or a tree. In Grasshopper terms, it would be like a tree of values, and we write it to a JSON file here. Point count with the date of now. I can just do it again. And then we do the same thing for a CSV. That we have a CSV with 3 dimensions, with 3 columns, X, Y, Z. And that's it. And when you go here, I just open up. This was all made by Colab right now, and you can see your things. This was the first monkey chair we did. This is this one, the CSV and the JSON. You can get both. Oh no, I already did that. I need the new one. Does anybody want to see something else generated before we move on to Rhino? Or shall we make a pause? Do you guys want a break before the Rhino? Okay, let's do a break. I'll see you in like 10 minutes or 15, as you wish. Okay, that is, yeah, in 10 minutes. 52, whatever, in 50, yeah. Five to eight. Yeah. In my case, it's 5 to 8, whatever your 5 to whatever time it is to you.
Zapraszajcie do pisania za CPU też. No. Ci bine cu surprizele de la Mișa. Nu, chłopaki rękowci z nas. I polecam sobie.
Okay, is everybody here? Can we start? Okay. Does everybody have a CSV? Or do you have like some wish other to train or to see? That's gonna, like, in the meantime, open up Rhino. I have a new computer, so I still have trial stuff on it. Oh, okay. Not much to see. You didn't miss much. I just opened up right now. So you try out. Yeah. First of all, install some stuff. Like the easiest way to install this stuff, which I found really handy, is like I have Pancake, but you don't need it right now. I just use it to see what I have installed. Not portability. Actually, yes. There was a thing in Pancake where you can see what have you got installed. All reports. Remove the analyze. It doesn't tell me anything. Okay, it's good. You just go to the package manager. And search for its CSV voucher. You can just go CSV. You should see it here. And alternatively, I don't know, like you can also probably get it from Rhino, but I just find this method much easier. And I think you would need to go to Rhino anyhow for pufferfish. And I don't think you, and Dendro. Yes, you need to go to a food provider. Yeah, so food provider, just like get pufferfish and Dendro. Yes. Can find CSV voucher on so I don't know, maybe some other page. Let's see. Never mind. It's in the package manager. Is everybody here? First thing is like now we have our points. We're happy with what we've done. Okay, that's fine. And now we need to like actually bring them here so we can get a 3D model and like a bit edited and like make it to our liking and so on and so forth. I can give you the monkey chair and the one we did now. I think so. I don't remember if Dendro is only Windows. I have only used Windows and Linux, so I have no idea. Yeah, and MetaHopper. You need MetaHopper. But that's in the package manager. Yeah, it's there. If you don't see anything, just include the pre-releases and you will see it. Pancake made some delays. Why is it not working? Okay, so is everybody set? Okay, so the thing is, you switch your path here. Just need to switch your path here. And this is for the JSON file. So the thing is, like, you can see, because there's a difference actually in how these files represent the geometry. Like in some cases, the JSONs represent the data differently than the CSV. That is due to how the points are saved or how the data is saved. So you can see it with both. Try it with both. So if I replace this path here, we need the actual path here to the item, and just this one, because here we just need the alt folder. So we need to copy actually this, but with a JSON. I'm doing the lazy way, or you can also do it like up here, like copy as path. Let's see, like shift right click here, shift right click, copy as path. But then, like, you would get this paths, the underscores, not the underscores, what's it called? Got the name in English. On German is Klammer. So, this is one of our monkey chairs. And maybe do the same representation here. No, this is the other one. This is a bit fancier because like it's more automatic, like it takes the folder path. You have to import this glob to read for the file name in glob to join the path it reads with CSV, and then like to print out the file name. So we get these two file names for each of the item. for each item in this folder path. That's our CSV, of course. And we like counted. This is where MetaHopper comes in, because we automate kind of this index selection. So like now we have only 2 items, but if we had like 3, 5, 10, the slider would be like automatically like adjusted. I think they should go bifocals because it's not so visual. I think, share the definition somewhere. Yeah. Just scroll up and you'll see the definition. So this is like get connected objects. So technically it just takes this slider and you have the list indices from pufferfish. Yeah, it's from pufferfish. You can just like Control Alt and see from where it comes. And it counts. You have like 2 indices here. Gets the bounds from 0 to 1. It's a range from 0 to 1. And it's like adjusting the slider to this range, 0 or 1, naturally. And then this data is being fed to the index. So like we can cycle through our chairs. This one or this one, and you see the panel being updated. And then comes the voucher, the CSV voucher. Get that from the package manager, as I told you. Because I didn't really see it in the food for Rhino. And we get our chair. Let's see if this one is the same as this one. Yeah, pretty much. But sometimes there's like differences between CSV and JSON. So I always check both. But now comes the fun part out of it. We like make this into like a solid thing. So the other thing with I use Dendro. I like Dendro. I mean, probably you can just go like the Lonely Mesh or something. It's a very wacky thing. Like you're sitting on needles or something. But we want to be more proper. We're going to be using Dendro instead. But for Dendro, like you can just start building it. At that point now, always start with these settings. We need to adjust the voxel size, the bandwidth, and all of these things. Those will be our settings. We need point to volume because the way that Dendro works is like with VDBs. If you have used Houdini, like you probably know VDBs, and Dendro works with this library OpenVDB. And that's why Dendro is like amazingly fast in what it can offer without too much struggle. And we need the points. We need some radius. Yeah, point radius. And for now, I mean, we can do we're gonna do actually later the proper computation. For now, I'm just gonna do the distance like this. That we have like a kind of overview on how, in which scale we should like operate. And take a slider out of it. That's 0 to 1 scale. This one is, you see, it's like based on the 0, so we can fix that, like just if you want we parameterize the points. Also pufferfish, and now it comes in the positive coordinate system. That's important for later if you want to do 3D printing or like position it anywhere else. It's gonna be very weird, or you'll have like a lot of struggles to get it to reposition it. It's manual work. So like, why not save yourself from it? And settings, yeah, these are the settings. What's it called? Oh yeah, because the voxel size is 1. The radius must be 33% larger than the voxel size. Okay, so this guy. Actually, this guy, if you see it's in the same domain. Needs to be 1.33, like 33% higher. So actually, it's the other way around. This guy is constant. This guy is larger. Maybe we can just like use the same thing. Like so. Okay, a bit more. 1.4. Okay, now there's something. Big blob. I know. But we can also do smoothing. Because now it's a volume, it's not a mesh yet. This volume. We can do smooth stuff. Volume. All these iterations. Zero, 1, 3. So we can just do a slider, dot, 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 3. And then give you a slider from 1 to 3. Very nice hack. It's a question to link Colab to Grasshopper. Not directly, not as far as I know. I mean, I have done it the hardcore way with sockets and stuff like that, but it's not worth it. Like, honestly, it's not really worth it. Because it's much easier, or like the workflow, it's much nicer if you just collab directly, because you see it anyhow in Colab. You have a preview, and it just like Rhino. Actually, it doesn't matter if you do Rhino. Like, you can also do it in Blender or whatever program that can just parse like point clouds. You can also do it in MeshLab. Why not? I'm just using Rhino out of convenience, that I'm just used to it. Does that answer your question? It's this. I mean, you can tinker around with this endlessly and just like maybe make a better way how to do the point radius and like measure the points and all of that stuff. You can get as geeky as you want here. You can probably be like, what's it? I don't think you would have it. It's a thing from Parakeet, I guess. I can't find it here. Fast closest points, yeah. And to try to be back to lower a bit the computational time. This to this one. Stop. Yeah, I mean, I did this with like pointy and a lot of tinkering. So like AI and these models are very, very, very unpredictable. Like, and I'm stressing this a lot. That's why, because it's kind of a black box, because it's not our own models. I mean, in order to train your own model, you would need like a lot of data. Like, and like for these, you need a lot of tinkering and messing around and getting the right output and stuff like that. So like, it's a bit of like very, very also luck. I would say it's also luck, because you never know what you're gonna get. It's not a it's not a thing like in Grasshopper you set with a thing like, okay, I'm gonna just like twin some curves and like rotate this and up this, and like you're always kind of in control and know what are you gonna what's gonna happen. In this case, you never know. You just want a I don't know, organic chair. What is an organic chair? I don't know. What are you gonna get? Still, I don't know. So I don't know. Like all the answers right now about these kind of things are very vague, I would say, for design purposes. And even if you know proper data science, generative AI and stuff like that, they're not made for design. Like, unless you train them, but still. And I mean, you have to answer the other question when you have the starting point of this definition somewhere up in the chat. And afterwards, yeah, of course, just share this. Because, and how about that? Does this answer your doubts? I think also Mike mentioned that in the beginning that like all of this is like very, very, very beta. Like in any case, so there hasn't been a model so far that's making precise uh, like models. So like you won't find it. I mean, that's what I'm trying to do, but it's very, very hard. Measure the points. I'm measuring like each point from it, each first point from each list, each tree branch actually, with each of the second one, so I get some distances, so I can use it as a base. So you don't have to like measure the thing, because like earlier I just baked the thing and measured it manually. But now this has to this it's a data, no problem. Think of yeah, maybe. Let's see if it brings us anything. Because here we have 4,000 points, 4,000 values. So this one. So here. Measure stuff. It doesn't like it. Okay. Okay, it's fine. We don't need this. We're not gonna pay this, obviously. It's not relevant. Right. From an image, we can do that later. Well, why not? That's also easy. Okay. Just make sure. Volume settings. Volume settings is a big thing here. And we have our panda thing that we did originally. This can be also better, like just quadrimeshing all of these things to get a better topology. But if we're not 3D printing it, we don't care, honestly. Maybe it can be like a bit fancier. Maybe you just follow it, make some cool structure in it. Anything, but like we can just try that with the other one. I think it was more representative. copy the entire thing. Let's switch this. I do this for the sake of like keeping the dendro settings, because if I move them, like they don't fit, it's gonna be a problem. Okay, I think this one is cuter for the next steps. What do you guys think? Do you want to experiment on this one or this one, or generate something totally new? Yeah, I think so too. It's better for, I mean, the first one could be also good. I don't know, but we'll see. Anyhow. Now, the easiest thing to do is like have our mesh. We're gonna make an animation. No? We're going into the part with the deep animation and stuff. So the easy way is to like I use KeyShot for the first steps, because like it's because we need an animation input, and mostly I use a video input to transform it into something else. And but nothing stops you to just use a single image or to use any other method. So like there's like multiple methods like that you can proceed with. So you can also like make an animation from Rhino, like just to turn the APO and like record this animation or something, or like do any complicated and do in this step, like you are totally free to choose what you want. At the end of the day, we need a video file of this somehow moving or replicating some motion that you want to showcase it with. So I just like live link it. I mean, you can also save it and like just drop it into KeyShot. I just do the live linking. Actually, I should have done it the other way around. Or not. Let's see if that works. Okay. Here it's second one. No. here I have everything set up. I mean, you need to switch to the animation. You just click here. All these tabs. It could be also like this. The important thing is here when you set the image, you should get like, I do it in 1024, like 1 by 1 resolution. 1024. The reason there's a thing here, you should choose either 512 or 1024, depends on the model you are working with. That's the thing, because like if you're using a model that's based on Stable Diffusion 1.5, then 512 actually is the resolution for you, or the best resolution, because Stable Diffusion 1.5 was like built on 512 images, and like if you're using the latest one, if you're using the latest Stable Diffusion, so it's built on 1024 images. So you can choose, and that's how you would build up your animation. And I just like make this into 15 frames, so it doesn't make, and there is this animation wizard, and I make it to 30 just for the sake of making it simple. And you just make this 5 seconds. It's okay. I mean, this can be however long you want to be, and however long your computer can handle, and how much you're willing to wait, because here it's about waiting time, and especially later when you plug it into the model, like if you have like a big animation, like 15, 20, whatever seconds, you will actually wait quite a while, unless you have a very beefy machine. And the thing is, like, especially then, you don't know what you're gonna get. So and our animation looks kind of like this. Okay, you can just like change the material. Let's see how that works. So maybe it's gray, so it would be better recognized by the algorithm, but I, I can make two and see how the model responds to each material. Because in this case, it's not about the visuals. Like forget the visuals. It's about how this animation is being perceived by the model. Okay. Render. untitled, and just put the date. It's the 6th. Okay. You might or might not need these render passes. But oh yeah, we're going to animation, and like KeyShot has like this. For our case, it's very weird. 800 by 800, so I'm gonna do this 1024. Untitled 60. You can output the frames or not. Maybe you will need these render passes if you want, because later you can like input them also in the animation. Of course, you can. The problem or the question is in which quality you can convert 2D into 3D. Depends on the quality you want and like and what do you need actually. Don't expect like details or very intricate stuff. Like it's not that easy. It's not a one-step process, I would say. It's still you need to know some stuff and it's a lot of research. But I can show you some stuff later if I have time. I'm doing that professionally every day for different causes. So. And it's okay, it's fine. Oh yeah, I want to render on the GPU. It's much faster. The CPU is a bit probably more accurate, but I will wait a lot. The GPU is much faster. That's fine, that's fine, that's fine. Okay, it's done. Now we want to see one. If it makes a difference later. Okay, it should be. Fine. Okay. How's everybody doing? On which step are you? Yeah, it doesn't matter if you have KeyShot or not. Like I told you, like you can just do like from Rhino, you can just do like Arctic modes and like turn go and just record this somehow. It doesn't matter like whether you have KeyShot or not. I just do it in KeyShot because it's a nicer output. Like just hide the mesh here, hide everything, like hide all these grids. Like I think in render mode, you can do that. I think it was just have to manually disable everything and make this mesh wires. Oh, and then biofilm, yeah. Yeah, mesh wires. Disable these things about the grid. Oh yeah, here. Grid, C plane. And just like and then just third table and somehow capture this. Okay, so maybe move on to the models. General, like my stable diffusion looks like this. And this folder, like where we have all these files. And the thing we're gonna run, you need to run, is this WebUI user.bat. I have it as a copy because I have been editing it a lot. I mean, this is a .bat file. You can just like open it with a notepad. And it's this like set Python, set git. It makes a virtual environment. It uses this virtual environment that I saw, that I showed you, which I opened. If I do this, like Anaconda prompt, run it as an admin, contact. I named it so. For you, it might be some other name. And cd to this folder. And run it from here. It's gonna be the same effect. But here I have all the dependencies. And so this .bat file runs actually this, because here I have all of these dependencies installed. And the important thing is here in these command line arguments that I have the API, this is very important, the exportments, and there are like medium VRAM, so it doesn't consume as much VRAM, and it needs to update all the extensions all the time, and every time I run it, and update the latest version, git pull. If anybody is familiar with git, like this is a very important command. And then like call the WebUI. And when I run it, yes, there is a new branch. posts everything, it updates everything. It's launching the web UI. Suppose if you try, we don't need it. Computer is already heating up, like 95% of my RAM is gone, I guess. With Zoom and all of that stuff. Okay, so stable diffusion heats up your entire system. You need to get this link, like Control-Shift-C. Control-Shift-C is the default copy in Linux systems. So, and in data science and machine learning, you need to use Linux a lot, like it or not. And you just like go. Okay, and you see, now Google disconnected me from here because I haven't been active in a while. And this is how the interface works. And there's a thing you need to do first. Actually, the models you have downloaded, you need to go put them into models and in stable diffusion. My models are huge. And when you have done that, like you are ready to restart the web UI, or just go here and like refresh it. Is everybody up to here until this point? I see only one yes. Okay, two, not bad. Civit AI. This one. And we need to go to extensions and like check for updates actually available. I don't need to check for updates because I updated instantly, like from the when I started. You need to load, and you need to search for like the forum. Okay, let's load the forum. Is it not here anymore? Okay. Okay, weird. I installed it from here, but probably they. But you can install from URL. Just go like literally here. And just like pass this link. Like pass this link. Install from URL and do this. And it will install it. So find it and install it. I feel old now. When I installed this stuff like a year ago or something like that, I don't remember. It was all available here, like half a year ago. I don't remember when it was. Now I don't see anything. Anyway, just like this. Install because it will lead you to this link. How is everybody doing? Did you install stuff? This should be fast. It should be like, shouldn't take too long. In the meantime, I can ask, you can ask questions for whatever we can discuss. Okay, somebody is done. The thing is, right now, we're gonna like put our video here. I mean, in general, now there are a couple of ways we can proceed. We can like, one option is like get this screenshot literally. And put it as like an image input to our image animation generator, however you want to call it. Or we can use the video that we generated. You can try both ways, actually. So we can also do, I think it's gonna be like, what are you using? Like, are you using KeyShot? Or since you have only frames? It's a question that you can do actually. The best way is just to either use Photoshop or take more. There is also this animation or setting here called tapeworm. I don't know if I can it here. That would just do these kind of frame animations and stuff. Or you can just use Photoshop or any online thing. I don't know. I have only done the frame animations from Rhino from a slider and then just like make it into a GIF or a MP4 or whatever separately. That's why I like KeyShot. At least it gives you the whole package faster. But you can use like in the package manager, I think you can find tapeworm. Yeah, tapeworm. I have it. Like, how do you access it? Access. Input outputs, yeah, source path, target folder, frames to GIF, frames to video, and you just go do all this stuff, and then you run it. Settings, and that's it. Okay, so getting back here. When we go to this one, we have this sampler here. Yeah, there's a like, this is also important in the sense of like, it depends on your, how the diffusion model will behave. I mean, and there's like a whole science within each of these diffusion models, these samplers actually. It's not a diffusion model in itself, but it's the sampler, which is like very, very important because that's the logic or the algorithm that's gonna drive the diffusion model, kind of. And like this is Euler ancestral and stuff like that. The default is it is Euler A. And I see a lot of people now, especially with the new stable diffusion, they use this TPM plus plus. I think it was the plus plus model. I don't remember. I use mostly your Euler. It's been good for me. And like here you can do this step, this kind of learning rate, let's call it, how much iterations would you get the image. And the difference here actually in diffusion models is that like you, for each step, the image gets more and more detail, or like more and more like processing, let's call it. That might not be detail. It might also get a bit worse, all right, but it will get clearer for sure. It would not. It would be better in like image quality as an image. Maybe not content-wise, depends on what you ask, but like clearer for sure. And like, yeah, you have the width and height. In right now I'm using the Dream Shaper, and that one is on 1024, I think. On 1024. You have to check it with civets. Yeah, it's a random seed. -1 means any seed. So it's on restore. You can do this, like if you're doing restore faces. I mean, this was a problem in previous stable diffusion versions where it still didn't know how to make proper human beings. And like you don't need most of these settings. Here you can actually tinker more, like either a 2D animation, a 3D animation, an interpolation, and video input. Like we are doing the video input now. So we don't bother with the frames and all of that stuff. And here you can do this, all of these, like zooming, rotation, angles, transform. Then this I leave to your creative interpolation, because this is you need a lot of tinkering for this, and it's more of an alchemic thing. It's more of like you have to try it out for yourself. There is no formula for this. And yeah, CFG, I told you, is very important. Here it's around 7, which is kind of the medium, like approachable or like acceptable rate. Yeah, the seed is 1, that's fine. You can do all these subseeds and compilers. That's none of our interest currently. The prompts. That's the important thing. We can do only one prompt, actually. We can just like copy this. I put it in a notepad. And for the sake of like simplicity, for now, we can only do one prompt, but this is a JSON file. So this one, and this has been closed like this, I think. Use one time water, and here we can do all prompt engineering things. So how do you want to transform our share? Does anybody have any ideas? Or we just do the same generic, what was it, 3D printed monthly chair? I'm curious what would happen, or like just a 3D printed chair. I know what we can do. Except the swamp bunny. We do the chair. But not tiny, of course. Highly detailed, intricate, sharp photo, all of that stuff, as it was. Unless somebody has a better prompt in mind, if some of you is a prompt master background. In it, we don't have. Here we did the video, obviously. And where's our video? This one. all of this, yeah, from frame to all, -1 is always 1. All of them, actually. You can also add a mask. So like if you rendered all the channels and the video mask, you can also add the mask. Or then we can also use the control net here, like or multiple control nets. So like for each frame, there will be like it will generate the mask, it will do the control net and all of that stuff. But that's like just very, very additional tinkering. Okay, so let's give it a go. Let's see if everything is okay. And you can follow the process here. It's running. How's everybody doing? No response. Everybody's busy. I know, because it's too big, like in general. There's a Zoom stream running and like a Rhino and like Zoom, and my GPU is overloaded. So maybe we should run it a bit slower. I mean, not on 1024. Sure. I'm gonna say goodbye. Something. No, nothing. It made 3 frames. just change the model. Here comes also the knowledge, like which model is like lower, like lighter than others. Just newspaper 7. Just lower. It has been changed. And here, then I switch this to fast now. Now, see what it says. Yeah, 12 games. Yeah. Does anybody have anything to add or ask in these 12 minutes? I would rather make another image or tinker with control length from this, from what we have. But the thing is, like, we can answer the point cloud to from an image question. Like, there is a script, like you can reverse the process. That's not a problem. The problem is like the quality and stuff. Right. We can just take our random screenshots, KeyShot screenshots, why not? Image with the background. I'm preparing stuff in the background, and this is rendering. So answer your image to print code question. Actually, you can just reverse the script. That's not a problem. Actually, you just do the same thing. Let's see if it works. Oh yeah, we need an image. Right. And just do this one. Why not? Let's see if it will represent it accurately. No. No. Capture the file. A bit more. Okay. Uh, Capture, copy the path. And put 3 on this. Smoothly. Get the crazy thing. can make this even crazier. Okay. Actually, here, bring this back in. And say here, anthropomorphic, no, the same thing. The depth of field, surrounded by vectors, why not? This kind of animation, why not? How much frames do we have? Six seconds. Like 30 frames per second. 15. That's right. Fine. So actually, I think we will make it for this one. Only these three. And we can morph it actually into a sofa. And then what else we want? And okay. I know. Be as creative as you want here. I need to. Yes, yeah. Always commas in JSON. What is it? this one. Uploads. It's set to the video input. As you see, it's rendering only a single frame. Are your paths correct? Is this? Yeah, it's like this. Okay. A bit blobby. Yeah, I mean, my laptop is currently under a lot of stress. Almost. Yeah, this part is a bit complicated for it. I mean, you can tinker with these parameters endlessly, and like it all depends on the computational power and speed and resources. So it's a very alchemic process, I would say. The top part looks satisfactory, I guess. No, not at all. The hole is missing. Afterwards, we can make a mesh out of it, but like if this extreme version, like why bother making a mesh out of it? Here comes the hyperparameter optimization and all of these things that I was talking about. Is my voice okay enough or not? Or the forum is taking the soul out of my computer. To hear what I said last. no memory to proceed. Yes, that can happen too. I haven't experienced it yet. I feel so with very manual. Control C, and it would in the process. So you just like run it again. Is my computer okay already? Okay, it's not too bad. Workable. Just restart it. And if the video is too hard on it, I have an idea. You can just like start with an image, do the control net on the image and do the deform on the image. Image to image. Like this, that. Open 512, okay. We're not going to torture computer too much. image. And now you want to control that. Now we have to enable it. I will do the lower VRAM just in case. And here you can do a preprocessor. In this case, I'll do the second. So in depth to extract the depth from this image. And here I will also do maybe the depth. So you have a preprocessor that would extract and make the map actually. And then you have a model that control that model. Resolution, weight, starting control step. Okay, that's all fine. I just want to see, yeah, allow preview. I wanted to do the same, but I guess it's too busy. Okay, we'll just run it without. You can just get the prompt. Ah, it's reset. Reset 3D printed share. Yeah, and all that stuff. Cats. Sofa. So on. Here we can take a table. Same here with the table. And as much adjectives here as you want. Okay, here 2D 60 frames. Ours was like I'll make it 75. A bit lower. CFG replicate. We don't need any of these inits. Nothing. We're not gonna use anything. I'm not gonna keep the images. Okay, let's see what happens. It's 512, 512, okay. Should be fast. Because it doesn't need to read the video and all these things. Okay, that sounds fancy. Oh, I forgot. I forgot the main thing. I didn't do the image to image. In the controller. And just interact this. I went for the prompt actually, and I got carried away. This is that. And as negative prompts actually. So you get negative prompts here. Logo. Watermark. Blur. It came out okay for start, I guess. We'll see. Okay. Being built up. There's okay. This was supposed to be depth. Never mind. Let's see what happens. You can also mix and match. Like it doesn't have to be like the processor layers and depth and depth. This can be also like empty. So like there's like a huge amount of opportunities to like think of it. Yes, you see the depth map and this. We have our fancy chair here. I don't know how this is 3D printed. But it's detailed and corpuscular rays and all of that things, all of those things. So you can just do like send this picture. And if you go here, image to image images, Here we get the image of the image. It's the image. Get back to this image. Everything stays the same. Yeah, this is our starting. And on the 30th frame, we should see it morph into a solver. Supposedly. And then to a table. Is anybody still with me right now? Are there brave warriors who have stood until now? Okay, so you three are the champions. Oh, the three people. At least, as I see in the chat. Do you have any doubts and struggles and stuff to ask? Transforming into a sofa cherry thing. Yeah, I see some. It should be a sofa now. Okay, now we have a cherry sofa. And I see. And now it should go towards the table. See doubts about image to a point cloud. Actually, the script is more or less the same as we did for the text tool. I mean, the first part is exactly the same. Like you just download the model, and all of that stuff. You can change the resolution. It's treated so you just upload an image. You open the image, and then it just trains right on the image instead of the training on the prompt. It's training on the image, because the image has values. Every image is a value. Every image is like a NumPy array of values. I mean, that's how computer vision works. Output is really there. There are like a lot of reasons for this. One being like the inadequacy of 3D model data, first of all, and second of all, like how much do you train it? Like computational power, time waits, all these kind of hyperparameter optimization, all these things that we talked about are like time scale much more complex, or take much more or time wise. So I then like just doing it for a 2D image, because a 2D image is flat. It doesn't have that much features and dimensions as a 3D point cloud or object has. Yeah, we know. You see, that's why you should do stuff at least locally, or pay for a Google Pro. Yeah, you see. think this one, yeah. Yeah. See it morph into stuff. I mean, this could be like much smoother if you had much more iterations here, much more frames. It would be much more smoother, and like you would see the transitions much better, and like all of these things. But that also like needs much more computation power, of course, and you would have to be much more present here. Oh, like okay. So, any questions?
It's not going to at the end.
Yeah, I'm very at the end. Yes. So like that's why I say like, are there any questions or doubts? Or do you want something to discuss?
As Im's asking for Jupyter Notebook.
Yeah. What's it here? My computer is having a hard time.
Zvonko, can you make a folder with everything and I can give it with the recording?
Yeah.
Well, very cool webinar, interesting results, and I hope everyone enjoyed it. It was a lot of fun to watch. If there's any last quick questions, feel free. Otherwise, you'll get the recordings and files after. Yeah, thank you so much, Zvonko.
From like, how did you listen to the whole thing?
Yeah.
Yeah. How did you find it?
It was very interesting. It's all very, very cool stuff. And like that you don't know what to expect, and
Yeah.
you expect this from this thing on your screen right now.
Yeah, that's the whole thing about any of these things. Like you never know what to expect. You just like input your general wishes, let's call it like that. But you never know what you're gonna get at the end. Almost never. But it will be along these lines. I mean, unless you're doing
Sims
like,
is asking if you can discuss your workflow from 2D to 3D.
right now, actually, like I do mostly like optimization stuff, like more proper data science things, like rather than design, like because like I don't really deal with the design or the aesthetics in my daily workflow. I'm mostly like in the tech side of like how to make these things work for like people to use and to tinker with them. Yeah. So that's why I say like you never know what you're gonna get because it's all how the model is trained and like how, because as a user, like you, as I told you before, like you just like ask for a random piece from that model, like, but you will never know what in which latent space or like which piece of that latent space you will get, because like you always get a random seed. I mean, at least you can ask for a specific seed, no problem, but like you need to know, like, I don't know, there's like a lot of uncertainty in this case. I mean, it's not a black box. I mean, depends on the case actually. If you're working for design and like aesthetics and stuff like that, it's mostly a black box. Because, but like if you're looking into like uh, optimization and numbers and like for this kind of predictions of panels and numbers and prices and all of that stuff, then it's like very like precise and concrete. Right? So that's solely depends on your use case.
Well, thank you so much, everyone, and I think we'll end it here. And looking forward to see some of you at our next webinars and see you next weekend, which Zvonko will also be a part of as well.
Yes.
Thank you, Zvonko.
Thanks.
See you.
Thanks for having me. Like this was cool. Like I enjoyed like tinkering with you. And see
Okay.
you soon, guys.
See you.
And we
Bye
see
for
you
now.
next week, hopefully.
Yeah. Goodbye.
Bye.